Why don't we get started? So today we're going to continue on with our discussion about processes, and we'll start things with a demonstration of some of the code that's in the book, particularly the POSIX interface for forking a child process. So there will be a homework coming out, and it'll involve questions about Chapter 3, so please look out for that. And so when we last left off, we talked about process termination, and this was some of the interface, rather the APIs made available for user programs as it pertains to process manipulation. And where we left off last time, a week ago today, we talked about how a parent or the relationship rather between a parent process and a child process. And we said a parent process is allowed to abort a child process. And we talked about a number of reasons why that might be the case. And then we also talked about this idea where we left off about cascading termination. If a parent process forks or creates a child process, and that child process creates another child process, and so forth, you end up with a tree structure, almost resembling an ancestry tree, where at the root is the first process that was in the system, and at the leaves are the last child processes that were created. And so some operating systems do not allow the child to exist if its parent has terminated. And on such operating systems, there's a so-called cascading child process termination that occurs, meaning that if you terminate a parent process, it'll go through and walk that tree of processes. So it'll literally traverse data structure in the process control block. One of the fields is a linked list. So it'll be pointers to elements of a list, and that list will contain all the child processes that that parent process has created. And so some operating systems will go through effectively walking that tree of parent processes and all of the ancestors, if you will, and go ahead and terminate all of those processes. Now, that's not guaranteed for every operating system. That's something for which you have to look up in the operating system documentation to see if it's supported. But some operating systems implement that as a convenience for you. Okay, so that's where we left off. Any questions about this? Okay. So let's continue on, and we're going to bring up VirtualBox, and we're going to try out this forking of process. And as we had discussed before, you create a process ID type, and this PID underscore T is a C struct defined in one of the header files made available for the programmatic interface from the operating system. And so when you call fork, it's going to literally make a copy of the process control block, the operating system will, for this particular process. And in doing so, if you were to look at the process listing on your system, whether it's the system information or doing PS command in Linux, you're going to see another process instance occur among all the processes that are running. So when this fork command returns, there will be two copies of the process control block, and therefore two processes made available in the ready queue and ready for scheduling by the short-term scheduler. And so this fork can return one of three different types of values. If it returns a negative value, that means that there was a problem with the forking. And so reasons for that might include inadequate resources on the system in order to create this new process, or there was some underlying issue with parts of your operating system and or, bless you, parts of the underlying hardware. So if the fork returns a negative number, that means that the fork did not work and you do not have a copy of your process, the process, i.e. you don't have a child process. Then fork can also return a process ID of 0. Now, when fork returns a process ID of 0, that copy of your process control block representing the child process is the one for which the process ID, when it's returned, is 0. And then if it returns a positive number that's greater than 0, that is the parent process, right? And so from the perspective of your program, it calls fork, and that fork is going to return one of two things. And if all goes well and there are no errors, one copy of the program is going to continue execution in this else if block, and the other copy, namely the parent process, is going to continue its execution in that last else block. Okay? All right. Any questions about this? Make sense? So it's a little bit to wrap your mind around when you're doing programming like this, because you have to kind of think in terms of the parts of the machine as if you have a parallel version of yourself. Okay, so let's pop out of here for now, out of the slides, and let's see, and let's bring up VirtualBox. Hopefully this works. I'm not going to use parallels today because my license expired and they want to charge me full price instead of the university discount. So I'm still waiting for uh, some communications to come back. So let's start this virtual machine, and it'll bring us up in Ubuntu. And we will, at the command line, select Ubuntu from the bootloader, grub, and we will, from the command line, enter in the program for forking a child process. So we log in. And if you're using VirtualBox, there has been an update. So I encourage you to install the update. So Control T. I'm assuming people can see that in the back. Okay. Okay. So let's go ahead and go inside that directory, Gary Holness, that I had created, where I'm doing all of my C stuff. And let's call it process test or proc test .c. So we're going to add to the make file. Oops. Let me remove make file.swp. Whenever you run this text editor VI, it creates a hidden file to let you know that the file has been opened by someone. So that's what that swap file was. Okay, so let's add a new default rule, and we're going to call that proc test. Right, so we're going to need a rule to compile proc_test.c into proc_test.o, the object file. Proc_test.o is the target. The dependency is proc_test.c tab, and the command gcc compile proc_test.c. Okay, so we have a rule for producing proc_test.o. Let's go ahead and add a rule for producing the proc_test executable. Proc_test executable depends on proc_test.o and tab gcc link together. The target of the linking is proc_test, and it's going to link proc_test.o along with the libraries made available by the operating system. All right, so let's save that, and let's now write proc_test.c. All right, so we're going to include a bunch of includes, number sign, include, sys, types.h, okay. And then it has a number of system types, things like PID underscore T and so forth. And we're going to number sign include standard IO, IO.h, stdio.h. And that's going to give us things like printf. And we're going to include number sign include UNISTD, UNISTD.h. Okay. And this is missing something. If you look online, it says that the wait that a parent process executes should be defined here, but there's another include called sys, I think it's sys wait, that you're going to have to include. So we'll get to that in a moment. Okay. So let me just go ahead and write the signature of the main entry point. So int main. Now, in the example in the book, it doesn't have arguments, but I like to have arguments on my main routines. So int arg count, arg c, char star star arg v. All right, so those are the counts of my command line arguments to the program, and as well as the array of character strings or char stars, so char star star, for the text of the command line options specified when I ran this, when I run this. So PID T, so I'm going to create a local variable called PID underscore T. PID underscore T is a C strut, so I'm going to use that. And PID is going to be the variable that I use to hold the process ID returned by fork. Now, you'll notice that I'm not going to do a memset of this. There's nothing incorrect by doing a memset. But in this particular case, it's going to assign by value the return from fork to this PID local variable. And so it's going to actually get a value assigned to it. Okay. So you could do a memset if you wanted to, but just to coincide with what was in the book, I'll just explain it and just type it in. So PID, that variable is going to get the process ID, which is a number, and that's returned from the fork function call. So I'm going to call fork and semicolon. So now when I execute that line, when that line is executed, there are going to be two processes that return from it. One is going to be the parent process with a process ID assigned that's greater than one, greater than zero, and the other is going to be the child process. And so now I'm going to check to see what happened based on the value of the process ID that was returned from fork. So if the process ID is less than zero, right? That means there was an error. And then I have an else if, and you'll notice here, I'm filling in the blocks for this three-part conditional, right? Uh, else if PID is equal to zero, so that's going to be the child process. And then finally else, that's going to be the parent process. And the only other thing that happens for the else is that PID will have a value greater than zero, like 1, 2, 3, and so forth. Else, right? And so I fill in all those blocks before I write in the behaviors that I want my processes, whether it's the parent or the child, to take. Okay. Any questions about this? Yes. Oh, yes, yes, you are correct. Thank you. Just seeing if everyone's paying attention. No, that's a bug. All right, thank you. If pit is equal to, so thank you. ID. Okay. Yeah, my finger was one above home row. All right, so great. So, all right, if your PID returned is less than zero, that's the error condition. And we're gonna do a print. And this particular print is a stream print called printf. And when you run any process, there are three streams that are available to you. One's called standard out, std out, right? One is called std in, and one is called stderr. Now, standard out, if you write to the standard out file descriptor or stream, it's going to take that text and put it out to the console so you can actually print out things. That's what printf is actually doing. If you read from standard in stream, that's going to take input from your input device, namely your keyboard. And if you write or print a text, fprintout, that stream print to standard error, it's going to also output to the screen, but it's not going to do any buffering. It's going to immediately print out to the screen. And that's used for error messages because if you think about it, when you have an error condition in your system, you want to alert the user at the console right now. You don't want it to collect enough text to fill a buffer, and then once the buffer is filled, the OS then pushes that out to the screen, right? So there's standard in, standard out, and standard error. And in this case, we're going to do a stream print, printf, to stderr, right? And these are actually numbers, but it's important to use the standard definition because it could change from one OS to the next. And then it's going to give an error message. And this text for the error message is fork failed. Okay. So now that we've handled the error condition, and if you think about it, what happens if the fork fails? Well, if the fork fails, that means you're not getting an identical copy of yourself. The process control block isn't copied, and you don't have a child process created. And therefore, the one who executes this first block in the three-way conditional is going to be the parent process. So it's going to tell the parent process, hey, this fork routine failed. Something is wrong with the system. And in this particular case, given in the book, it just returns from the parent process because that's considered a runtime failure, and you want to actually stop your program after alerting the user. So we're going to do a return of 1. And recall that the main routine, that main entry point, that has a return type which is integer. And the practice in Unix is that if there is no error, you always return a 0. If you return something that's non-zero, like 1, 2, 3, and so forth, always has to be a positive number. That means that there was an error condition. Okay, and many of your command line programs that are scripts, they return error conditions, and you can search on the internet for what standard error conditions are. Each number means something different within a certain range. Okay. Any questions about this? Makes sense. All right. So let's now look at the case, or rather the second block in the three-way conditional corresponding to the child process. And so if the fork command returns process ID of 0, this block is where execution will continue after the fork. It'll continue for the child process. And so this is going to execute another program. And so what happens is you fork. That means you make an identical copy of the process control block. One copy is for the child, one is for the parent. And at that moment, it's a same identical process running, only two different copies, except one of them, the child process, has a value of PID of 0, right? And so the two processes are exactly the same, except the parent and child differ in the value that was returned to this local variable PID. So at this point, we have the child copy, and the child then can load another program from disk and actually load that into memory, overwriting, or rather filling in the PCB process control block information with the new information for that program that is running from disk. And so there's another command called exec, right? And that says to go ahead and execute some program. So we're going to call exec LP, and I'll leave it to you to search in either in the Linux manual pages for what the command line, the API calls, the parameters mean on exec LP, or you can Google search. There's lots of stuff available for free that'll tell you what it means. Okay, so this exec is going to run bin ls, and ls is the program on the Unix command line or a built-in command with most Unixes to give you a listing of everything that's on your file system. So you're actually going to see in the local directory a list of all the programs or files. And in this particular case, in the Gary Holness directory, I have the make file and I have a bunch of object files and C files. And so you'll see it print that out to the screen when it runs. All right, so let me finish this call, and it's going to return a null here to the parent process that called it. And so again, this is the child process. And one thing I can do, let me go ahead and add a printout here. Printf, oops, printf, child process here, right, \n, right? So the child process is going to print out a message before executing that long listing, okay? All right, and then let's, yeah, so, okay, so that's the child process. So let's go ahead and go to this third block for our three-way conditional. And let's fill that in. And so again, when execution jumps to this block, that's for the parent copy. That's the parent copy, to remind you, has a process ID returned from fork, which is a positive natural number. Okay, and so the parent is going to wait for the child process, so it calls wait. And in this case, we're going to specify null instead of the address where it should send the return value from the child process. All right, this is to mimic exactly the example in the book. And then it's going to print something out, it being the parent process. So printf, parent says child complete, \n. Okay. So here we have the fork command. The child block is going to print something out. The child is going to print something out and then execute a listing of the directory. The parent is going to wait for the child and print something out saying that the child has completed. And then after all that, the parent is going to return normally from its main method back to the operating system that called it, or really the program loader. So I'm going to return 0, meaning that there were no errors if you come down to this part of the program for the main routine. Okay. Any questions about this? Make sense? Yeah. And so you might be wondering, well, gosh, you said the parent returns 0. What about the child? Okay, that's a good question. So recall when the child is called, right? The child copy has a PID of 0, and the child immediately prints child process here and then executes the long listing, the ls command. And so that ls command is a C program, or was a C program. It's an executable. And so as an executable, it runs and then returns a 0 if it's successful. And so because it runs and returns a 0 when it's successful, when the parent calls wait here, the child has already exited when that wait unblocks, right? So it's going to stop and wait for that child to exit. And remember, when this exec LP is called, the child copy of the process control block is going to be overwritten, if you will, with all of the information for this ls command or this ls program, and no longer this test proc program. Right, so it's going to be completely different code, if you will, that's running, but it starts out as an exact copy of the parent. Okay, so let's try this out and let's see what happens. All right, so let's just run make. No rule to make target proc test. Okay, I misspelled it. Let me go back into the make file. Oops, wrong one. Make file. Oh yeah, 2 T's. Let me get rid of that copy of the T. So proc test. Okay, so let's try this out. Write and quit. Let's make clear. Make. Okay. Oh, yes. Okay, I totally forgot about that. Implicit declaration of function wait, right? So that means it didn't have a definition for this wait function. So let's go back into proc test. Oops. And let's go into the includes, and let's include sys wait.h. Number sign include sys wait.h. Okay. And so they chose to split some of those routines as it pertains to a parent process waiting for a child out into a separate header file. Okay. So let's try make again. And we see that the compilation is successful. So let's run proc test. As we can see, the text, it starts out the child process here. So the child starts executing. So remember, the child process is created as a result of the parent process forking, right? And so the parent process forked the child process, right? It forked, it cloned itself. And then the parent process immediately went to wait for the child, right? And so if the parent waits for the child to exit, the parent doesn't do anything until the child is done executing and exits. So that means you're going to see the text for the child first. So the first thing you see is child process here. and then you see all the files that are in the directory. That's the bin ls. That's the listing that the child process executed. And then after that, the child exits. So once the child exits, the parent unblocks or continues executing as a result of waiting. So the wait resumes, and then the parent then prints out what it prints, and it says the parent says child complete, right? And so text-wise, all of this text up to and excluding this last text output, that's the child process producing that text. And then the parent process is producing this last line of text before you get the command line prompt. Okay. Any questions about this? Does that make sense? So you can imagine, well, you might want to ask yourself, and time check, why would I ever want to do this, right? And so a process is, bless you, a unit of scheduling, right? And when you have a process running, recall that each process, when it's in the ready state, it exists on the ready queue, and it is scheduled by the short-term scheduler for execution for some amount of time, delta t, on the processor. And so the unit of scheduling is the process. And if you have more processes in your system, you're effectively making more efficient use of your CPU, right? Because some processes might want to interact with the network card, might want to wait for input from the keyboard to block for I/O, and so forth. And so if you have a program, right, and your program is going to accomplish a set of things, so you might want to partition the behaviors in your program into those parts that interact with certain parts of your I/O on your system, and those parts that are mostly compute bound, those things that just do calculations on the processor, right? And if you do that, then and you can separate them as separate processes and have them scheduled separately on the processor so that those parts of your program that need to block, i.e. go into the wait queue for each of those I/O devices, can actually do that, while those parts of your program that are just doing calculations on the CPU that are compute bound, so-called compute bound processes, you can have more parts of your um, application running at the same time, right? And so a process is a unit of schedulability, and you can sometimes, or sometimes it's important, it's good to partition the behaviors of your program into individual units, if you will, sets of functions, each one of which is callable from a main routine that you devote to separate processes. Okay? All right. Any questions about this? Does that make sense? Okay. All right. So let's uh, power this off, and let's continue on with the other material. All right. So I'm going to try from the tablet so I can actually see it in front of me and see if that works. Not really sure, but we can certainly give it a try. I have it up on the tablet. Let me run my mirror server. If it doesn't work, I'll just do the slides from, I don't want parallels. So let me do that. Mirror, cross your fingers, rebroadcast. Nope. Okay. It's not going to cooperate. I don't know why. All right. So let's just do it from here. Current slide. Let me just get my remote so that I'm not bound to the desk for the entire time. Oh, did I? That's right up there. Let's see. Oh. And hopefully the batteries didn't die on this. Well, that works. There we go. Okay. All right. So we just talked about an example of fork and the semantics of how the fork works and what happens in the parent copy of a process and in the child copy. And so the parent may wait, doesn't have to, but it may wait, and it's good practice to do that, to have the parent wait for each of the child processes that it forked. And so recall in the process control block in the struct task in Linux, we had one field, and that field was a pointer to struct task, and that was an array, or at least the beginning pointer to an array of process control blocks for the children of that process. And so, as a parent, you brought them into this world, so it's your responsibility to wait for them when they exit. Okay, and so we had this wait that we talked about, and then we saw an example of, but we used null as the parameter for that wait. Now, if you did not use null, what you would put is the address of that process ID structure, and that address is where this wait routine, when it exits, it will write the status of the child process. And so we didn't use that facility in the example. I just wanted it to match what was in the book. But the full-blown treatment is for the parent to obtain somehow the exit status of the child, and that's done as the parameter. So you're specifying a pointer address of status, and status is an integer, and it'll write that status, exit status for the child in that location. So if your child returned a 2, maybe there was some error condition, then in that status variable as the parameter for the wait, it's going to write to that address that value of 2. Okay, so we didn't do that on the example, but there are lots of examples. I recommend you Google search and tinker with it and try it out for yourself. Okay, so what happens if your parent doesn't wait? So if your parent doesn't wait, you still have a child running, but there's no way for that child to really tell the system gracefully that it is exiting what that exit status is, and that's called a zombie process. And so a zombie process is a child process whose parent did not wait for it, right? And then you have something called an orphan process. That means that the parent, I didn't come up with these names. These are the names that people have developed over the years. But if the parent process exits without waiting for the child, that child is left without the parent, so they call it an orphan process. Okay. Any questions about this? Does that make sense? Now, of course, if you're on an operating system that gives you this cascading termination, you can't get orphan processes, because simply by the parent exiting, the operating system is going to walk that tree of child processes, the whole ancestor tree, if you will, and it's going to, in kind, terminate all of those children and the children of children and the children of children of children and so forth. Okay? All right. So let's take a look at one example of partitioning program behavior into a set of processes. One of them is the Chrome browser. It's a product from Google. And I don't know, I don't have information on which version of Chrome did this. Maybe it still does. I'm pretty sure that it uses threads for many things today, but at some point, maybe for some things, maybe still now, it uses processes. And so oftentimes, a browser will run as a single process. And as a single process, that's particularly bad if you think about what can happen to a process. So you're a process and you're in the ready queue, and your short-term scheduler picks you to run for some small amount delta t on the CPU. And then the first thing you do if you're a browser, okay, well, certainly you're going to use the network card to reach out, whether to push out data or to get back data through the network card. So all of a sudden, you do a read on the network or receive, and then that requires you to wait for I/O. So you're going to block, and you are kicked off the processor, and then now your process is waiting in the wait queue for that particular network interface. Now, of course, what happens? Well, a process, a program, if your browser is a single program or single process, it has a lot of different parts. The browser can be drawing stuff on the screen. It could be calculating something if you have one of these, like JavaScript or Node.js or something like that. It could be, doing all sorts of stuff, pushing stuff out to the printer. But as a single process, if it blocks because it's trying to get something from the network card, the whole process is now in the wait queue, right? So that means that process, other parts of your program, those parts that want to do things like draw stuff on the screen, it can't do anything because the process is in the wait queue waiting for the network card. So in that case, it would behoove you, be wise, to have one process, your browser comprised of a bunch of processes. One process could be off drawing things on the screen. Another process could be interacting with a network card. Another process could be interacting with the printer. So now you take your browser code, right? You say, gosh, well, parts of my code are going to look at the network card. So I'm going to make that a separate process. Another part of my code is going to be interacting with the printer. I'm going to make that a separate process. And then I have the renderer, the thing that draws stuff on the screen. I'm going to make that a separate process. It's going to interact with the graphics card. So then if you block waiting for I/O for, say, the network card, but you're not blocked as it pertains to the printer, as it pertains to rendering, then those other parts are schedulable and can be selected for execution off the ready queue. And different parts or more parts of your program behavior can execute on the processor rather than halting the whole thing. Does that make sense? Any questions? So we have Chrome, and it has multiple processes, and it's partitioned to three different types. There's the browser process, which deals with user interaction. So interacting with I/O devices, as well as the user interface and the network I/O. Right, so they partition that part because it's certainly going to block any time you want to interact with the user or interact with the network. And then you have the renderer process, and that's the thing that draws all of your web pages. So it interprets things like HTML, and it has the semantics or the behavior routines that do things or draw things based on what the HTML says. And likewise for JavaScript, it parses or chops up JavaScript and implements that runtime behavior for whatever the JavaScript program might be. And then you also have the plugin process, right? And so the plugins are these add-ons that can do all sorts of stuff, and a separate process does that. Now, a plugin comes from a third-party source, third-party meaning not the manufacturer. So if something is buggy in an add-on, you don't want it to crash the browser, you just want that plugin to crash. And so if it's going to crash, you don't want it to bring down the whole browser, right? So what would happen then is you start your browser, and that would be that first process for the browser, and it would go ahead and fork three different child processes, one of which is used for browsing, another of which child is used for rendering, and another of which is used to interact with the plugins. And so then that parent process will create three children, and that parent process would then wait for the exit status of each of those children. So for example, if your plugin process crashed, then your parent would get the exit status for that plugin child process and say, hey, wait, I waited for it, and wait returned, and I got an exit status that meant that there was an error. So I'm going to go ahead and either restart it or post some error message that says this plugin crashed. Okay? Any questions about this? Make sense? Yeah? All right. So, moreover, some web browsers will start a separate instance of all this machinery for each tab, right? And so when you create a new tab, that's like creating a new browser, right? And some will even go further and say, let me repeat a whole instance of my browser process associated with each tab. Okay. So let's take a look at interprocess communication. And if you have parts of your program, right, that are implemented as separate processes, now certainly if you're going to interact with the network card in a browser, that means you're going to either be sending a request or getting back the HTML and JavaScript for some web page. So if your browser has a process that interacts with the network, at some point the renderer is going to want to draw the web page on the screen whose text was just given to you across the network. So that means that you need to have these processes be able to communicate with one another to send information. And so a really important construct is so-called interprocess communication. Now, interprocess communication can be between processes on the same machine, right? Or it can be between processes on different machines, right? And so certainly on different machines, you think of the internet, right? But on the same machine, you can take some liberties because you don't have to go across the network or interact with the network card when two processes are communicating on the same machine. And the reason for doing that is it's much faster to go through memory than it across the bus than it is to actually go out on the network card. Okay, and even if you're using sockets, for those of you who are familiar with TCP/IP communication, or maybe you've taken networking, there's a speed up called the loopback address. So that if two programs are communicating on the same machine, you use a special address called the loopback address, and that will underneath the covers use shared memory to implement the transfer. So two processes on the same machine, they could be independent. They never need to talk to one another. Okay, that's all fine and good. Or you could have two processes that need to cooperate. And the example I just gave is you have those parts of the browser that interact with the network card talking to that part of the browser as a separate process that draws things on the screen. Right? They need to share information. And so cooperating processes more formally can be affected by the outputs and the inputs of other processes. Okay, so at some point your processes are going to need to cooperate, and so you might do so because it speeds up computation, and that's an important one. You want to parallelize a problem. One way to parallelize a problem is you have more processes working on that problem, and you start out, you take the problem, you divide it up into a bunch of chunks, and then you give each chunk to a separate process, you let them run, and then when they're done with their sub problem, they return their answer. So for example, suppose you want to sort a list, or you want to find the maximum, the largest element in a list. That list has a lot of elements. So you decide to divide the list into two parts. Literally, you just split it in half, and you give one half to process A, the other half to process B. So now process A and B are running, scheduled on the processor. They each get time on the CPU. And now because you have two processes, your task, as it were, gets 2 units of time devoted to this process on the CPU. So now process A finds the maximum in its half of the list, and process B finds the maximum in its half of the list, and now they return back what their maximum are for their halves, and then you just decide which one is greater, putting the two results together, and then you return the result, which is the greater of the two maxima. Right? And so certainly the more processes you have, the more units of execution on the CPU you have, you're making more efficient usage, and you can speed up your execution time for a problem through this so-called parallelization. And so you might want to have processes or multiple processes interacting with one another because you get speed up of computation due to parallelism. But go to grad school, you can take a whole semester just on parallel computation, and I hope you do. This has diminishing returns, and it's called the overhead due to parallelism. Because as I mentioned, in order to parallelize the problem, you have to chop it up into pieces. Well, that takes time. And then once you farm out or you execute those pieces of the problem or execute on those sub problems, you then have to collect together all of those sub solutions into a single solution. And all that takes time. And so what this overhead due to parallelism says is if it takes so much longer to chop it up and to gather the partial results than it does to actually execute, then parallelism at some point will actually slow down your computation. So please know that this computation speedup has its limitations, right? You can't just arbitrarily parallelize. And people spend a lot of time analyzing a problem to say, does this overhead to chop things up and to gather partial results, does that have limiting returns, right? Can the speed up more than pay for, or is it faster than the slowdown introduced by the parallelization? Okay, so of course there's information sharing, and the browser is one example of that. Modularity, so that if parts of your program fail, you can recognize that failure and take action. And then also convenience. Sometimes it's a lot easier just to think of parts of your application as being separately scheduled entities. Okay. All right, so cooperating processes need a way to communicate, or IPC, interprocess communication, and there are two major flavors, if you will, of IPC. One is using shared memory, right? And it is, as the name implies, you're literally taking a piece of RAM, you're saying, keep this piece of RAM around so that any process that comes along can actually access it, and you're using that piece of memory as a way of exchanging that information between the two processes. And so you can use shared memory, and you can also use message passing. And the two are slightly different. And in fact, if you think about what network communication means between processes on different machines, that's just a fancy way of doing message passing. Okay? All right. Any questions about this? Okay. So this is an example or schematic, and it's in the book, that describes at a high level. Let me do a time check. Yeah, all right. That describes at a high level what the two major flavors of IPC, interprocess communication, looks like. And so here on the left, your left, frame A, we have an example of message passing. And so for message passing, the operating system kernel sets aside a region of memory, and it's a message queue. And whenever you want to send something to another process, you deposit your message into this message queue made available through the kernel. And so whenever you want to receive a message, you're going to pick off a message from this message queue, first in, first out behavior made available by the kernel. And so this idea of a message queue, one process produces a message and the other process consumes the message. And so because this thing is carved out of memory, right, or some special buffering made available by the kernel, this message passing in real terms has finite amount of storage, right? But you could actually have special message queues that are backed partially by disk as well as RAM, right? Have some caching going on and get pretty large, pretty long message queues. Now, in enterprise application development, message queues, or sometimes they're called message buses, message channels, are really, really important, right? And when you deal with these enterprise like Java Enterprise Edition and other types of enterprise software, enterprise message queues are how you get parts of a system in enterprise application to communicate with one another. Okay. All right, so that's message queue. On the right, frame B, your right, we have shared memory. Now, shared memory, as you can see, is part of RAM, and that region of RAM is set aside, and it's off limits now for heaps, right? You can't go ahead and allocate out of the shared memory. It's set aside a priori for usage for communicating or interacting or cooperating processes, right? So the shared memory effectively is what's called pinned, right? So you have a region of RAM. It's off limits to anyone. So when you say malloc some memory, the system memory controller does not allocate those regions of RAM to processes occupied by this shared memory for message passing, designated for message passing. So we have two processes, A and B, and we have our shared memory message passing mechanism. And A would write some value or data structure in this region of shared memory. And to A, it looks just like memory, but it's not really traditional memory, so to speak. It's this shared memory for message passing. And B would then read this message, this data structure out of that shared memory. So process A might produce some data structure, and process B would consume this data structure. And as you can imagine, in each of these cases, process B, if it's consuming these data structures, it needs to know, is A, done writing, right? So you also need some coordination between the two, a form of synchronization, which is subject, I think, of chapter 5, okay? So we have these two flavors for communications. We have message queues and we have shared memory. Okay, and so if you have these independent processes, they can't be impacted by the execution of another process. That's what independent means. Okay, that's all fine and good. But if they cooperate, that means by definition, one process affects the behavior of another. So in the case of a browser, if you have one process that interacts with the network card, it gets some HTML. Well, the values or the content of the HTML that network process receives is going to impact what the rendering process does, right? So they absolutely impact one another. Okay, and so this IPC, it's really important for all sorts of reasons. I think we talked about this. This is repetition, convenience, and a bunch of other stuff. All right, so um, this introduces an issue, right? We talked about this need for synchronization. And so this need for synchronization between the two cooperating processes is often posed as a so-called producer-consumer problem. One process, whether it's a message queue or it's shared memory, one process is taking a data structure, some information, and it's putting it either in the shared memory or in the message queue. So it's producing some information. The other process is taking that data structure or that information out of that shared memory or message queue, and it's doing something as a result of it, right? And that's called consuming the data. And so This message queue, whether it's a message queue or shared memory, it's a type of buffer. It's storage. It's parts of memory that you can use to put information and from which you get information. It can be unbounded, meaning that there's no limit on the size of the buffer, or it can be bounded, meaning that there are a fixed number of slots, if you will, in the buffer where you can store information. Now, of course, we saw something like this bounded buffer when we declared an array of structures. We said you have 10 of instances or positions in this array. And therefore, once you filled the 10th position, you no longer could use it because it was already filled. And if that's the case, well, you have to now wait if you want to fill it some more with a new copy of information. You have to wait for the consumer to take that information out, making a slot available for storage, right? And so this idea of producer consumer is a way of thinking about how two processes might interact. And you can have two different scenarios, an unbounded buffer or a fixed size or bounded buffer. Now, certainly in real terms on an operating system, there's no such thing as unbounded resources. You can kind of give the illusion of unbounded resources by backing something that's in memory, in RAM, with specialized regions on disk. And so effectively, you're implementing a form of caching and presenting it as if it were in RAM, but really parts of it are on disk. Because the good news is this has some locality principles, right? If you're going to access a data structure in position I in an array, a certain position, it's very likely your next access is going to be nearby if it's a FIFO queue, first in, first out, right? So that means if you're going to access something and part of it is on disk, well, you know ahead of time what the next access is going to refer to. So you can then pull up another block from disk and put it in RAM because you know ahead of time what's going to be accessed next. Right, so there are ways of giving the illusion of unbounded buffers, but in real terms, you have finite resources on a system. Okay, any questions about this? So this is a pseudocode, and this pseudocode represents the idea of a bounded buffer. And so you have some shared data. And in this particular example, they're using structs, but they're using a type def. So that's something that we hadn't covered yet, and I'll certainly cover that in the next sitting of this class on Thursday. But type def is a convenience so that you don't have to type struct structure name every time you want to use it, right? It's another way of abbreviating the definition of this user-defined type mechanism in C, okay? And we'll talk about that. But nonetheless, you have a user-defined type. It's a data structure, and you decide what you're going to have inside of it. Doesn't matter what it is, but it is a C struct. And so here, item buffer, right? We have a buffer of buffer size many, in this case, buffer size is 10. So we have 10 many copies or an array of these user-defined types, and we have enough space to hold 10 many of these C structs. So this is a bounded buffer, and the solution is fine, but you only have 10 copies in this example, or excuse me, enough space to hold 10 of them. And so when you're producing an item, usually what happens, you use what's called a circular buffer. And by circular buffer, what I mean is that you can imagine that you have your array and you have the first position, which has an index of 0, and then you have the last position, which has an index of 9 if you have 10 spaces in your array. And when you get to the 10th location, the next location you're going to store in is going to be position 0. So you can imagine this array kind of wrapped around so that it's circular instead of a straight line, right? So once you come off the edge, at the end of it, you go back to the beginning again. And you can see that in this modulo arithmetic here. And so here, we continue in a loop for the producer, and the producer is the one who's going to deposit this data structure into this bounded buffer, and this is the bounded buffer case. And so you sit in a loop and you produce the next item. And what you do, you say, okay, well, if the place or location in is where you're going to put things, that's an index, and out is where the consumer is currently grabbing things. So if in equals out, that means the buffer is empty, right? Because the consumer is in the same location as the producer. So that means you don't have any more space. So You check to see if the input location, if the next location is currently where the consumer is, because you don't want to overwrite before the consumer has gotten its copy, the consumer process. And so you do nothing. You execute what's called a spin loop, right? You sit in a tight while loop doing nothing, and the nothing command is just semicolon. It's how you terminate a command in C, but it's also, you can have that stand alone as a so-called nothing operation. Now, this is a very expensive thing to do because when you have a spin loop like this, the do nothing in a while condition, you're actually executing cycles on the CPU but not getting any work done, right? And so we'll talk about signals and waits and blocking operations in the future. But nonetheless, the producer does nothing if the place where it's going to input or add records to the shared memory bounded buffer is in the same location in the array of where the consumer is trying to take it out of, right? So you can't overwrite what has not yet been consumed. So then if you can produce the next one, then it goes ahead and it produces its data structure. In this case, in the pseudocode, it's next produced, and then it inserts it in the buffer in that location marked by in, right? So in might be position 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and it wants to go wrap back around to 0. But if the consumer is currently consuming something from position 0, it's not going to override it until the consumer is done. Okay. All right. And it does that in this case with that spin loop that checks to see if the input position in the array is the same as the output position from which the consumer is grabbing things. Okay, so then when we come down to the bottom on the next iteration, it increments input by 1, and then, excuse me, does modulo the buffer size. And that's where the circularity is implemented. So once you get to 9, if buffer size is 10, in plus 1 is 10, modulo 10 is 0. And to remind you, modulo just means the remainder, okay? And so this is how you'd implement this bounded buffer. On the producer side, that's the process that's putting data into the shared memory. Okay, any questions about this? Make sense? Okay, let me do a time check. 30. Okay, we have about 15 minutes. So let's take a look at the consumer side. And the consumer side, this is pseudocode, and it's in the book, and that's the behavior that describes what the process that's getting this data, that's responding to this data. And so in the example, excuse me, for a browser that we talked about, this would be the renderer, would be the consumer, and the producer associated with that would be that process that was getting the HTML from the network card. So we sit in a tight loop, and we have a do nothing spin loop here, and the consumer says, okay, well, am I trying to take out of this buffer a data structure or information that is the same position where the producer is trying to add? So that means the buffer is empty and you're right at where the producer wants to add something, right? So if there's nothing to consume, you don't do anything. In this particular case, we have a spin loop. And again, this isn't the best thing to do because it's a waste of CPU cycles. But at this juncture in the course, that's perfectly acceptable. Okay, so then it goes to the buffer. Once there is something for it to consume, it goes to position marked by out, and then it takes it out of the buffer, makes a copy of it. Okay, and so once it does that, now the producer can go ahead and rewrite or write over that space because the consumer has now taken that out. So the next thing that happens is that it increments this out. So out gets out plus 1, and it does it modulo the buffer size. So again, if the out was at position 9 in 10 position array, 9 plus 1 is 10. Modulo buffer size, modulo 10 would be 0. So it wraps back around. It's a so-called circular queue. Okay? All right. Any questions about this? Make sense? Yeah. Okay. So this is what the producer consumer looks like for the bounded buffer. And whenever you have a bounded buffer, you make that buffer, that queue, a circular queue. And the effect of this modulo arithmetic on the positions within the array where you do the producing or do the consuming, that modulo arithmetic implements that circularity on the queue. Okay. All right. So let's take a look at shared memory approach for doing IPC. And so shared memory is an area of memory where processes that wish to communicate can exchange that information, right? And so literally you're going to pin this memory in place so it's not going to go away when the process exits. And therefore each process that comes along is going to so-called attach this memory so that it can access it. Right? So one process would write something to the memory, it would produce data, and the other would read something from that memory, it'll consume that data. And so this is under control of the user processes. The operating system has no involvement in this. The only thing that happens with the operating system is when this memory is set aside for sharing, the operating system notes down, okay, this is off limits for allocation. So if someone calls malloc, I'm not going to allocate that to some other process because it's being used by two other processes or more processes for this specific purpose. And so the issue here is that you need to synchronize. You need these processes to coordinate because to each process, it just looks like a piece of memory, like as if you called malloc. And if that's the case, well, you now need to indicate, well, the producer is now writing something in there. Hold off, don't read anything yet. And likewise, if the consumer is reading something, it needs to mark, the producer needs to mark, well, don't consume yet because I'm still writing something in this memory buffer, right? And this is done often in image processing pipelines in computer vision, because if you think about it, especially, excuse me, if you have a high definition image, you can't afford to read and write this thing to disk each time you want a process to operate on it. Typically what you do is you keep it around in shared memory. One process performs some operation on that image, it's kept around in memory, another process attaches to it, performs its process on it, and then it's only once you're done with each stage of processing that you then write this out to disk, right? So this is used all the time in computer vision. Okay, so we're not going to talk about the synchronization that's coming probably in another couple weeks, but certainly it's a very important consideration. How do you know when a certain process is allowed to either produce, write something in, or consume, read something out? Okay, so you need a mechanism to allow processes to communicate using shared memory. And the messaging system provides such a mechanism, right, without resorting to shared variables. And when I say shared variables, these shared variables, in the case of shared memory, are used to coordinate, right? Because you need some common knowledge in order to coordinate. And that common knowledge is made available as if you mallocked it from each process, but underneath the covers, it's really the same piece of memory. And so for the messaging system, it provides these very clean operations, the send and the receive. So the send inside the kernel, it places a message onto the message queue, and the receive removes a message off the message queue. And so the nice thing about having these entry point APIs is that you can implement this locking, this coordination inside of the API implementation. But with shared memory, it's a little bit more tricky because it just looks to each process that you have a pointer to memory that you mallocked originally, right? That's what it appears like. Okay. Any questions about this? Make sense? So these messages, they can be anything. They can be a basic type like an integer or a float, or it can be a user-defined type, a struct with an arbitrary set of fields. It can be fixed size or it can be variable size, right? It's wide open. Okay, and so if two processes want to communicate, they establish a link, right? And this link could either be an identifier or it can be, a unique address, and then they communicate. Because one of the issues, if you have a message queue, is you have to know, gosh, well, to whom should this thing be delivered, right? Is it intended for a single process to be the consumer or multiple processes? Especially when you're in an enterprise environment, it becomes a really important consideration, especially if you have protection issues or security issues associated with it, right? So this idea of establishing this communication between two processes, P and Q, sometimes you do so by establishing a link. Sometimes you have some identifier, or sometimes some message bus systems do what's called publish and subscribe. It's a way of identifying the intended recipients of a particular message in a message queue. Okay? All right. Any questions? Make sense? Yeah? Okay. So One of the issues, a lot of practical issues, if you're implementing these message queues, how do you establish these links, these endpoints of the communication that identify who is the sender on this channel of communication and who are the recipients that can get it? Can you have point-to-point communication, one process, process P to process Q, or can you have multi-point communication, one process communicates to more than one process? You have this notion of groups or multicast, as it were. And how many links can there be between a set of communicating processes? What is the capacity? Is there limitation on bandwidth? Right? Because you have finite resources, you can't have two processes hogging all the available bandwidth that you can use to send data, because that might not be the only process that needs to use this coordinating process facility. Is it unidirectional or bidirectional? Do you need separate links for each direction of communication? Process P sends a message to process Q, and then process Q sends a message back to process P. If it's unidirectional, you can keep it simple, and simple means fast. If it's bidirectional, you need additional mechanism to allow for that two-way communication. Because when you do two-way communication, the definition of the sender and receiver change. It's reversed. And that requires more machinery underneath the covers to manage all of that. Okay? All right. Any questions about this? Does that make sense? All right, so lots and lots of issues with IPC. And this IPC, I'll end here, can be implemented, the communication link, in many different ways. It can be physical with something like memory or using the hardware bus. And the nice thing about those is that it's very fast. You don't have a lot of layers of abstraction getting in the way, because each layer of abstraction kind of hiding the details of the underlying implementation from you, it adds slowdown, but it makes it more usable, and it makes it easy to now bring to another machine, to port this to another implementation, because the details of the hardware are hidden. You can also have logical, right? Logical through this idea of some kind of addressing scheme. That could be, an IP address, or it could be just a unique naming system where you have an identifier that uniquely identifies, like a UUID, universally unique identifier that identifies a particular endpoint that can participate in this communication. Okay, so each of these has benefits and drawbacks, and we'll touch on a little bit of it, but I more so just want to make you aware that this IPC doesn't come for free, right? You can have it as shared memory, or you can have it as a message queue, and you need to coordinate. The message queue gives you some ability with this send and receive API call to implement inside the runtime this coordination, but it's not as fast as shared memory. Shared memory requires you to coordinate or synchronize between the processes, because you don't want the producer to overwrite something that the consumer hasn't yet read. Okay? All right, so we will end there, and we'll pick back up with this on Thursday, and perhaps go over an example at the Linux command line with using shared memory. Okay? All right. Any last questions? No? All right, so I will see you all on Thursday.